Hello there, and welcome to our unit on chemical reactions. So in this unit, we're going to be looking at different ways in which chemicals can change from one form to another. And of course, this is the fun of chemistry. This is where all the action is. Everything from your campfire in the backyard, if you have one of those, that's something that we have fun with it at my home. And these are glow sticks, also good fun for the kids, to the grass growing and all sorts of biological things that are involved with chemical change. So how do you know you have a chemical change? Well, the main thing is that you get something new, a new substance that wasn't there before. So in order to identify that, some things to look out for, a new gas, and we'll look at some ways that you can tell if you get a new gas, a new liquid, a new solid, of course, and the other one is energy, something like heat or light that can indicate that there's been a chemical change. So a few signs that you have some of these changes. You can look for bubbles that aren't the result of boiling, so bubbles that make that show that a new substance is formed. Different smell, so when you're cooking and a chemical change occurs, you'll smell something different at the end of your cooking than you do at the beginning. New solids, of course. This little fun activity definitely makes a new solid that's totally different from what you started with. If you look in the bottom of your fire pit after your fire, definitely different solids than what you started with there. Precipitates are fancy words for solids that form under solutions, right? So that yellow solid that forms in this reaction is a precipitate. And of course, new solids, in order to distinguish them, will have to have a different color or some distinguishing feature that allows you to actually see them. New liquids. Of course, there are chemical reactions that produce water as a product, like your neutralization reactions. And again, with liquids, you're going to need some way to distinguish them from the other reactants that are around. So if it's new water, we might have to include an indicator to see if a chemical change is taking place, because in an aqueous solution, adding more water, you're not going to be able to see that. So we'll get to the places where that will be necessary. Temperature change, right? So obviously when you light a fire, there's a lot of energy that's being released, and also light that goes along with it. And so there you go, a bunch of ways in which you can tell that a chemical change has taken place. So when we're going to represent a chemical change, we're going to use the old method of writing reactants and then an arrow and then products, right? So those are going to be the equations that we're going to use. Sometimes it'll be words, sometimes it'll be formulas. And also we can include balancing as we go along. The arrow itself means reacts to produce. So in this case, we got good old photosynthesis here. So we got carbon dioxide and water react to produce. And then we have our new substances, the glucose and the oxygen. And sometimes over top of the arrow, you'll have either symbols or words to describe special conditions or other requirements that are needed to make the reaction happen. The three different types of chemical equations that we're going to use in this course. The ones with words, aptly named word equations, of course have words for the reactants and words for the products, but you still use your arrow and your plus signs to show the various components or separate them. For a skeleton equation, all you do is you replace the words with formulas. So hydrogen is H2 and it's a gas, and then oxygen is O2 and it's a gas, and water is H2O and it's a liquid under standard conditions, of course. And that would be a skeleton equation. And then finally we get to balancing, and so to balance this there's a couple different methods, but you start off, of course, with your same skeleton equation, and then you throw in some extra coefficients. These guys here are coefficients. to balance out the different parts of the atoms that are in the equation. To make predictions about the state of various components in your balanced equation, there's a few guidelines you can use. For elements, you can check your periodic table. You can see the red ones here. They're colored red to denote that they're gases under standard conditions. The blue ones here, they're your liquids. The black ones are your solid, which is most of them. And then these outlined ones, these are all not found in nature. You have to make them in like a nuclear reactor. And they're fairly unstable and they don't last very long. So that's why we don't find them in nature. For molecules, tends to depend on their polarity and size. So the really small ones, especially nonpolar ones, they'll tend to be gases. Anything with like an OH group on it tends to be liquids, and then larger molecules, they'll be more likely to be solids. And then, whether or not they're in water is another thing that you could look at to determine if it's going to be soluble or not. Likewise with ionic compounds, pretty much all ionic compounds are going to be nice hard crystalline solids until you put them into some water, and then a bunch of them will be able to dissolve and some of them won't, and we'll learn later on how to distinguish between the two. Alrighty, so over top of the arrow, sometimes you can add conditions that are needed for a chemical reaction to take place. Obviously, if I take some methanol here and oxygen and just pour it into a dish, it's not going to work. So to get a chemical reaction like this going, you're going to need some heat. So you can write the word heat over there, or sometimes they use a triangle to indicate heat. Sometimes it's a chemical that's needed to get the reaction to go. So for the elephant toothpaste one there, that's just hydrogen peroxide, but to get it to break down fast enough to see the reaction, you have to add a catalyst in. The common one that we use is potassium iodide, so you can put that over the arrow as a condition for the reaction. It's not a reactant or a product, but it does help the reaction to go, so that's why it goes over top of the arrow, not in the reaction. All right, so conservation of mass. So one of the cardinal rules of the universe here is that you cannot create or destroy matter, only change it from one form to another. And so to do that chemically means that you're going to always have the same amount of mass before and after a chemical reaction, as illustrated in this little balance here. So we have this could represent nitrogen, and this could represent hydrogen, and over here we've got some ammonia that is formed. And the mass of the nitrogen and the hydrogen has to equal the mass of the ammonia that is formed. You can't have atoms appearing or disappearing out of nowhere. So in order to reflect this in our equations, that's why we always have to balance. And so there's, of course, different ways to balance equations. The balancing by inspection is probably the easiest way for most reactions. And what you do is keep track of how many of each element you have on either side, and then you add coefficients in order to balance them out. So if I have 2 nitrogens here, and I only have 1 on the other side, I'm going to have to multiply this whole thing by 2. But remember that the coefficient applies to both of the atoms in the compound. So 2 times 3 is 6. So even though we balanced out the nitrogens, our hydrogens aren't balanced yet. So now we have 6 hydrogens. In order to balance that out, we're going to put a 3 over here. 3 times 2 is 6. When the right side and the left side are the same, you did it. Yay, ding, 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 it's balanced. One method that I find interesting and have used a couple times, wouldn't be my expectation for every student to do this, but you might find it interesting, is to use algebra to balance your equations. So if you ever get stumped, you can give this a shot if you like algebra. So what you do is you put in variables for the coefficients, and then you make true statements about the elements that are there. So let's say for hydrogen, we know that hydrogens on the left have to equal hydrogens on the right. So that means 2 times whatever A is, because that's a 2 there, has to equal 3 times whatever C is, 3C. And then for nitrogen, we can do the same thing. We know that 2 times whatever B is has to equal 1 times whatever C is, right? Because there's only one nitrogen on the other side. And then you can make a total one for all atoms. Sometimes you'll need this, sometimes you don't. And so we can say 2 times A plus 2 times B has to equal, this is 3 plus 1, 4 times C. And that would give us all of the atoms altogether. So now you get all these little algebraic expressions. And then what you can do is make yourself a let statement. So you can say, I don't know, you can pick any one of these and make it a value. So let's say, let's let B equal 1. I'm just looking for it here to an easy one, right? You can make it to any number and any variable. It just might give you a bunch of fractions that are harder to deal with. So I chose B because I see here 2 times B equals C, and I can do that pretty easily. So if 2 times B, or 2 times 1, equals C, that means that C equals 2. And then once I know C equals 2 and B equals 1, then I can go back up here and I can figure the last one out. So then 2A equals 3C. So C was 2. So 2A equals 6. And A equals 6 divided by 2 equals 3. So that way we figured out what all three of them were using algebra. So again, I don't require this of my students, but I still think it's kind of cool to share, and mathy type students might really like it. So then you can put the values back in here. You got the 3 there. For the B, we got a 1, and you don't really need to put that in. And then for C, it's a 2, which is what we got by inspection before. All right, there you go. Hope that helped. See you soon.